Good morning, everybody. Welcome. My name is Chris. It's my absolute pleasure to be here this morning with you to present this talk, Defense of Technical Excellence. I want to start just by saying thank you to NDC. What a great conference this is. Hope everyone's having a great time and seeing some excellent talks. So when I first started mentioning I was thinking about doing this talk, a few people said, like, what do you mean? Why does technical excellence need defending? I mean, don't we all want to be excellent? Sorry, get the clicker thing going. There we go. Like Bill and Ted on their adventure. We want to be excellent to each other. We want to be excellent to our code, excellent to ourselves, to our customers and stakeholders. We want to do good work, right? Who wants to do good work? We want to do work that we're proud of, that has a positive impact in the world. And everyone's like, yeah, I agree with that. But I don't know about you, I've been feeling that this kind of motivation is under attack. It is under attack. There are things happening that are sort of preventing us from achieving these objectives that we might have for ourselves. So I wanted to put this together, sort of explain how I think about it, and hopefully to give you some language and some ideas and tools that you can use to advocate for practices of technical excellence in your organizations. So let's go back to the beginning. I want to explain a bit more about what I mean by this. What actually do I mean when I say technical excellence, and what kind of attacks am I talking about? I'm going to illustrate this with a couple of stories. Let me know if you see yourself in these stories. So we start off, some stakeholder in our organization, maybe your product manager or your CEO, pops along and says, got a great new idea for our product. It's going to be brilliant. Customers are going to love it. I'm going to throw it in the backlog. That's the Jira icon, if you are fortunate enough to not be familiar with it. And so the team comes along, software team. This is us. We're getting together. We want to start working on it. And yeah, we start coding. We know what to do. We know how to code. We're going to build this thing. It's going to be great. Then our friendly QA engineer comes along, throws a stick of dynamite, blows the whole world up, and finds a bug. And we say, okay, that's fine. We can fix it. We know how to code. But we understand coding produces bugs. We're going to fix the bug. But we get told, no, we haven't got time for this. This feature is too important. Our customers need it. They need it now. So it goes to production, bug in production, bug bottom of the backlog, as I sometimes like to call it, the never going to do it backlog. And there we go. We go on with our world. Who's been in this situation? Show of hands. Yeah, like pretty much everybody, right? Next story, similar kind of start. We have our stakeholder comes along. Great new idea for our product, going to throw it in the backlog. Team, get started. So we come together, we say, actually this one's a little bit tricky. I'm not sure we can do this straight away. We're not sure how to do it. We're going to get a whiteboard, some sticky notes. We want to do some brainstorming, some design work. We get told, what is this, 1979? We don't do big design up front. This is waterfall. We're Agile, man. We're a rocket ship. We're going straight to the moon. Fuck off with your design work. Get straight coding. So we do. We get started coding. We go to production. We just leave a little stinky mess in the corner for some future poor person to deal with. Who sees themselves in this story? Yeah. I wish there weren't so many hands going up every time I give this talk, but it is what it is. Third story, same sort of start, stakeholder, new feature idea, throw it in the backlog, team comes along. We get started coding because we know we're not going to get given permission to spend time on design. Of course, we encounter our friend, the stinky little pile of garbage in the corner, and we sort of hit a standstill. What are we going to do? We're stuck here. We've got some technical debt slowing us down. But we press on. There's some delays. We don't quite get it done in the time frame that we hoped for. And then our friend, the QA engineer, comes along, finds another bug, which was more likely because of all of the difficulties that we had getting this thing done in the first place. And we go to production, but that stinky pile of garbage in the corner is bigger, and we've left a stinkier mess and present for our future selves. Who sees themselves in this story? Yeah, all the hands going back up again. It's a shame. This is really common, and this is what I mean. This is the attacks that I'm talking about, the things that are preventing us from doing the work that we know is the right thing to do. Now I'm going to take a step back for a moment and do a sort of like a meta-analysis of what I just did. I shared those three stories with you, and they are an example of what I think is this thing called an intuition pump. So Daniel Dennett is a really wonderful philosopher. He wrote this book called Consciousness Explained. Now, the title's a bit optimistic. I don't think if you read this book, you're going to come away thinking we've fully explained consciousness just yet. But there's a great idea in here, and it's this idea of an intuition pump. I'll read it for you so you don't have to read it. They're thought experiments. They're not really formal arguments, stories, little fables. They're supposed to teach us something. what they do is they lead the audience to an intuition, a conclusion. You sort of pound your fist on the table or throw your hands in the air and you say, yeah, it's got to be that way, doesn't it? It's a persuasion device. And I persuaded you all, yeah, technical excellence is under attack. Now, the reason I draw attention to this mechanism is because I think actually at the heart of this experience that we've all shared is a different intuition pump. And it's this one called the iron triangle. Who's heard of the iron triangle? I discovered recently in some parts of the world it's called a golden triangle. But it's this idea that there's an inevitable trade-off. We've got scope on one corner of the triangle, schedule, and cost. At least this is how it was originally formulated. And the thing about it in the original formulation was that quality was held in the center as this kind of like immovable goal. In fact, the framing of it was the quality of the work is constrained by the project's budget, deadlines, and scope. The project manager can trade between the constraints, but changes in one constraint necessitate changes in others to compensate, or quality will suffer. I'm like, I have never heard the iron triangle invoked in this way. Quality is never the thing that people are trying to hold on to, right? I don't think this is an experience that we've had. So I got curious into the history of this. Where did it come from and why is it expressed in this way? And it turns out this formulation was the original one, which was created by Dr. Martin Barnes. He was working in civil engineering. He was doing a PhD in what they call project control, contract control type stuff, project management. And he formulated it in this way. He put resources at the top. Cost, resources, and time on the 3 points with quality in the middle. Who wants to guess how long it took before quality stopped being an immovable goal and became one of the trade-offable constraints? If you guessed 1969, congratulations. So just a year later, Dr. Martin Barnes presented a training course, Time and Money and Contract Control, so sort of proto-project management. And yeah, he put quality on the corner. I don't know why he changed his mind. Not able to ask him. And maybe this was appropriate in the field of civil engineering. But he did this and explained it in this different way. And there's been many different formulations since then. In fact, it's really often quite ambiguous. And it tends to get invoked in a way that suits the purpose of the invoker, right? This is why I mean it's an intuition pump. It's not a formal argument. It's just, this is what I believe to be true, so this is what we're going to do. So sometimes it's scope, sometimes it's quality, sometimes it's performance, or the goal that you have, or the product that you're trying to build. The one thing that they all have in common is that there's two points which are like the inputs to the process, so cost and time. This is what we're providing to make it happen. And the thing on the other end is the outcome. So there's this trade-off. You can't have something for nothing, right? You've got to put stuff in to get something out. And in fact, there's a colloquial expression that I'm sure everyone's familiar with, which is good, fast, cheap, pick two. And in fact, in this formulation, this is one that I actually often see engineers using as a way of defending themselves from ridiculous expectations. We can't deliver the whole world in 2 months with a team of 2 people and an intern. It's just not possible. You want that outcome, we're going to need more time or more money, more resources. And that's reasonable. It's intuitive. It makes sense to us. And I don't begrudge anyone from sort of representing it in this way. But I think there's some fundamental problems with the application of this intuition pump in software development. So to explore that, we're going to dig into a field called systems thinking. Has anyone come across systems thinking as a practice before? A couple of hands. So there's this brilliant book, Thinking in Systems by Donella Meadows. Came out quite a while ago. Still very relevant, very well worth reading. More recently, there's another book by Diana Montalian called Learning Systems Thinking, Essential Nonlinear Skills and Practices for Software Professionals. Both wonderful books. I recommend you get a hold of them. We're going to draw on some ideas that are contained in these books, and in particular, an idea that I really like called causal loop diagrams. We're going to be using a tool called Loopy, originally created by Nikki Case in 2017. Since 2020, been maintained by Millicent Bietz. And it's an open source tool, just runs in the browser. I'm going to share the link to this slide afterwards, and you can click through and see these diagrams and actually play around with it yourself. So let me jump over here, and I'm going to show you what it looks like to actually build a causal loop diagram. I'm going to use some simplistic examples at first to sort of explain the building blocks. So when we're building a causal loop diagram, we start with understanding what are the quantities in the system that we're trying to model. So we're going to talk here about rabbits, population of rabbits. In a system where we just have the one quantity, I can increase the quantity and I can decrease it, but nothing else really happens because it's not connected to anything yet. So let's take a look at what happens if we connect it. We get 2 nodes. So where do rabbits come from? Baby rabbits. Let's say if we increase the number of baby rabbits, we're going to get more rabbits. So this is a causal relationship. from one node to another. What we're saying with the equal sign is that it's a causal relationship where the trajectory is the same direction. So you sometimes see it modeled with a little s for same, or a plus, which represents like it's a positive relationship between the changes. So it's all about change. If one side goes up, the other side goes up. If one side goes down, the other side goes down. This is a really essential component in these concepts. So this is important to understand. One side goes up, the other side goes up because of the equal sign. So it's a same relationship. That kind of model where there's just the two nodes, nothing really interesting happens. But when we introduce a loop into it, we do start to get some interesting behavior. This is why it's called a causal loop. So if we have more rabbits, baby rabbits, we're going to get more rabbits. We have more rabbits, we get more baby rabbits, right? Cause and effect in both directions. And as a result, we end up with an ever-increasing number of rabbits. This type of feedback loop where we have at least two, or rather an even number of equal signs on the connections, we end up with what's called a reinforcing feedback loop. Because whatever starts happening gets reinforced by the loop, so it continues to happen and to grow. And eventually, either you hit the limits to growth and you run out of resources and you can't keep growing, or what can happen as well, because remember, it's a reinforcing loop, it's about things keep going in the direction they were going. If we have less baby rabbits, we're going to get less rabbits, which means less baby rabbits, which means less rabbits, until the population declines to nothing. So it's not always about growth. It's about reinforcing the direction of the change. This is what's called a reinforcing feedback loop. We've got examples of this in our daily life. So maybe you've got a savings account with an interest rate on it. You get some money, you get some interest, that gives you more money. You've got more money, so you get more interest income, which gives you more money. It's a reinforcing loop, right? And I'm sure you'll think of many other examples as you start to sort of think about these patterns. It's something that happens, and because of some feedback loop in the system, it causes more of the same thing to happen. So there's a reinforcing loop. The other type of loop that we see is what's called a balancing loop. And this happens when we introduce a new kind of connection, which is an opposing link. So we've got a same link or an equals link. So when there's more grass, we're going to have more rabbits, but it doesn't go the same in the other direction. More rabbits means less grass. So what happens in a balancing loop is, as you might expect from the name, they balance each other out. And we actually end up with a sustainable system, something that's not static, doesn't stay fixed, wobbles back and forth around, kind of a sustainable range of values. And this is what we're usually looking for in systems, social systems, technology systems. If you've ever built a production system with an auto-scaling group, you've seen a balancing feedback loop in action. When the CPU gets too high, something kicks in and adds a node, which reduces the average CPU across the whole thing. And so you'll see the CPU wobbling like this, because when it gets too high, the feedback loop causes it to start to decline. Gets lower, there's probably a threshold that maybe removes a node, CPU starts to go back up again. It's a characteristic of a balancing loop over time. And these things are good. We like these things. They make systems sustainable, rather than if we've only got reinforcing loops, as I said before, it either expands into exhausting all of the available resources or it declines to nothing. There's another kind of reinforcing loop called a competition reinforcing loop, which is what happens when you have two opposing links. Now, I said before, if you have an even number of equal signs, then you have a reinforcing loop. In this case, we do have an even number of equal signs, which is 0, technically even, I guess. Maybe not mathematically in some structures. But what happens here is we get more hares, which means we get less rabbits. Less rabbits means there's more room for the hares, so we get more hares. So it's still reinforcing because one side is growing to maximum capacity, the other side trends downwards towards 0. They're both being reinforced in the same direction. It's just not the same direction in every part of the system. One of my favorite examples of this is if you've ever gone out to dinner, you've seen two restaurants side by side. Whichever restaurant picks up the first group of customers is going to appear to be more popular, and so the next group of customers will go into that same restaurant. And it could have gone the other way, just as in this case, if we had started the simulation by saying we've got more rabbits, that's the one that would have grown while the hares declined. And so it's a competition loop, but it's still a reinforcing loop. So the key concepts here are we've got causal connections. There's a cause and effect from one side to the other that is either an equal sign that says it's the same direction, or an opposing sign, which means it's the opposite direction. And if we construct loops with an even number of equal signs, we'll get a reinforcing behavior. And if we have an odd number, we'll get a balancing behavior. And we can connect all these things together. So what happens if we have a loop, a bunch of loops here? So we've got a reinforcing loop between the rabbits and the baby rabbits, balancing loop between the rabbits and the grass, similarly between the hares and the grass, and a competition loop between the rabbits and the hares. It takes a little while for it to settle, so I'm going to speed this thing up. What you see is the characteristics of a balanced system. Nothing is growing and being pegged right at the top, and nothing is declining to zero. So when you do have balancing and reinforcing loops in the same system, if the strength of the balancing loops is strong enough, they can compensate for the runaway effects of the reinforcing loops, and we end up with sustainability. Now, I've been talking about rabbits and hares here for a little while. You might be wondering, what's this got to do with software? But when I talk about sustainability, hopefully you can understand why I think it's relevant. Just a brief detour before we get into software. This is a wonderful diagram. I love this. It's from a book called Event Storming by Alberto Brandolini. Has anyone used event storming? No? A couple of hands going up. I'll talk a bit more about it in a bit. But this is an example of a causal diagram explaining things that happen in an organization. So we start out with silos and hierarchy, which increases the cost of consensus. So he's used the plus signs here. They induce fragmented knowledge, which increases the cost of consensus. We've got targets and bonuses, which increases conflicting priorities. Silos and hierarchies lead to local goals and issues, hidden agendas, again, increasing cost of consensus. We've got fragmented knowledge and cost of consensus, which are leading to decisions piling up. We've got fear of breaking invisible things, all of it trending towards a clogged organization and people wondering how we got here. So when I show this diagram to people, a lot of people are like, yeah, this is where I work. How do you know? Like, did you come and see our place? But no, Alberto had just seen a lot of organizations and he constructed this thing. And I share it to sort of highlight that you can use this concept of relationships and causal connections to model a lot of different things. And it can help you make sense of what's going on in your organization. In this case, the orange text is the impact of applying event storming. It brings visible expertise. It makes things visible in terms of the invisible things. It exposes inconsistencies and gets all the key people in the same room. It might not make sense right now what I mean by that. I'll explain in a moment when we get to talking a bit more about event storming. But let's think about these causal loop diagrams in software development. So a naive view would have us think that software works like this. We get new requirements, we get new software, we get new value delivered to customers. If only life was so simple, right? This is, I think, how some engineering managers believe the world to work. But we know it's not like that. We know that we're going to have bugs. And when we have bugs, we're going to write new software, it's going to be new bugs, and those bugs are going to decrease the value that's delivered. So this isn't a loop yet, but we are seeing a cause and effect that if we're not paying attention to quality, we're not going to get the value delivered that we want to. And we look at this sometimes, we go, well, that doesn't make sense. My intuition doesn't align with that. And there's this fear that often is used to sort of prevent you from fixing the bugs. That if you do spend time fixing the bugs, that it's going to take away from the time spent adding value. And so ironically, it's like, well, we're not getting the value we wanted because of the bugs, but also we don't want to reduce the time that you spend adding value or writing new software, so we're not going to let you fix the bugs. And I think this is exposing like a real sort of lack of clear thinking around what's actually going on here. But even this is not the full story. But actually, before we get into that, can anyone tell me, like, from what we've just explored with the rabbits and the hares, what kind of feedback loop is going on in the middle there? Is it reinforcing or balancing? I'm hearing some balancing. Did I hear balancing? Yeah. Yeah, exactly right. Because what's actually happening, and this is an interesting phenomenon, is that because we're spending time fixing bugs and not adding value, we're actually decreasing the rate of new bug production because we're not like adding new code. It's a pretty simplistic model. We know that we might be adding new bugs when we fix a bug. That's what happens to all of us. But this idea here that there is a balancing loop here which actually sort of steadies out the system. But it's not enough. People are like, well, we still just want you focused on trying to get that value out. Now, there's a few things that they're missing, I think. Sometimes you see people say, oh, can't we just fix the high impact bugs? Maybe most of the bugs are like low impact, so we'll just let them accumulate. We will fix the high impact bugs. And you end up with the similar kind of structure or flow of the system change. You will get new value delivered, but there's going to be times where the value isn't delivered because the high impact bugs are there. And yeah, okay, we're going to fix them. It's going to take some time away from the other stuff that we thought we were going to be able to do. But again, this is still not quite doing it for me. It doesn't quite tell the full picture. And it doesn't really explain to me the phenomenon that we see. And I think it really only starts to make sense when you start to introduce and recognize the presence of the feedback loops in the system. And there's a really strong reinforcing feedback loop that I've modeled here with the concept of confusion. Let me speed this up a little bit. We've got new requirements, we spend some time adding value, we get high impact bugs which we fix, we get low impact bugs which we don't fix. Those low impact bugs that stick around, they cause confusion. They continue to grow the confusion in the team. The presence of more confusion increases the rate of new high impact bugs and new low impact bugs because it makes it harder for us to change the code. So this is the presence of the reinforcing feedback loop. There's this naive idea that we can just do some things and not others and not pay attention to the fact that we're growing the confusion, and that confusion actually is part of a reinforcing loop that increases the problems that we have. And so when you speed this one up, we've got maximum confusion, maximum bugs, minimum new value being delivered. And this is kind of representing that first story that I told you in a causal feedback loop kind of style. There's another sort of set of models we can explore, which is not so much about bugs, but around cruft. Familiar with the term cruft? You might have heard it expressed as technical debt. I don't really like the phrase technical debt. I think it's misused in a lot of cases. A lot of people use it now to explain like shortcuts that they've taken. If you go back and look at where the term came from, Ward Cunningham introduced it, not so much to describe taking a shortcut, but to explain the value of getting started before you fully understand the problem, because you're going to learn things along the way. And so he sort of said that technical debt is the gap between what we've built and what we would have built if we had known then what we know now. That's very different to, we're going to cut some corners and just to hit a deadline. So I think that cruft is a better term for the kind of cutting corners thing, because it's just a catch-all for anything in the code that we don't like that makes it harder for us to engage with the code. Confusing design patterns, lack of clarity, inconsistent conventions, all that kind of stuff. And it's inevitable, right? Whenever we start working on software, we're going to introduce some cruft. So similar to the bugs, we're going to end up with a situation like this. But the difference is that there's a perception that cruft doesn't really affect customer-facing value. It's just an issue for the developers. So, maybe we don't have to worry about it. But since you're here and you've been listening to this talk, you'll imagine that there's more to it than that. There's a fear, of course, that if we spend time refactoring to clean up the cruft, that is going to, take away from time adding value, which is going to reduce the new value that we're delivering. But much like with bugs, there's this other quantity of confusion that we need to model. And because of the increases in the crufts, we're going to have increases in confusion. We're going to increase the time spent making sense of things. Okay, so this is a start, but I haven't yet got the feedback loop in place. So let's look at what happens when we recognize that more confusion increases the cruft. Well, you can probably predict where this is going by now. We end up with a lot of cruft, a lot of confusion, a lot of time spent making sense of things, and very little new value being delivered. So this is kind of that second story that I told you with the stinky pile of garbage growing in the corner, represented as to what happens over time through these causal feedback loops. Now we can put it all together into the sort of mega diagram. We got crufts, we got bugs, we got vain efforts to get new requirements delivered and value to customers. But what we see here, you combine it all together and we end up with a pretty sorry state of affairs. Lots of confusion, lots of angst, lots of time spent understanding things, lots of time spent fixing problems, and not a consistent or not a high grade of actual business value being delivered to customers or our stakeholders. I mean, I love looking at this diagram, don't get me wrong, like it's hypnotic, but it's a problem. So one of the things that's going on here is I think there's often a confusion around what we mean by quality. So I really like some work that Martin Fowler did to explain the difference between external quality and internal quality. So external quality, the quality that affects our customer experience. Maybe it's missing functionality or some confusion UI design or something like that. Versus internal quality, which is cruft. Confusing software design, tight coupling, low cohesion, poor abstractions, I said before, inconsistent conventions. This is anything that actually hampers our ability to make sense of and to change the code. And so if we separate between the external quality and internal quality, sorry, there's a link there on the slides to the original article that this idea comes from, we sort of can recognize that internal quality is invisible to stakeholders, but as we've seen through those diagrams, has significant effects. They're felt in other ways through this quantity of confusion. Cruft begets confusion. Confusion is the key part of the reinforcing loops that mean things just get worse and worse and worse if we don't address them. So what does this mean? Is that if we're looking at the iron triangle, we've actually got a reinforcing loop between two corners of the triangle. When we think that we can do a trade-off, that is an example of linear thinking. It's thinking that there's a predictable linear relationship. We cut a bit off here, we get a bit over there, and everything's fine. When we introduce the feedback loop, we have to engage with non-linear thinking. We have to recognize that this is not a linear relationship. Change on one side is going to cause a continuous feedback loop that's going to cause it to grow and widen and get worse and worse over time, as illustrated in those diagrams earlier. So we have to throw the iron triangle out, at least with respect to internal quality. I actually don't mind continuing to use it as an intuition pump for external quality, but I think we need to recognize that difference and to hold on to internal quality as a separate thing that cannot be traded off in the same way. So now that we understand what's going on, we understand the attacks that are happening, we understand why they're so bad and the problems that they cause, where does the defense come into it? How do we actually protect ourselves from the kind of patterns that lead to these bad outcomes? How do we protect internal quality? Here I'm going to turn to a wonderful article, and it's called Programming as Theory Building by a guy called Peter Now. He won the Turing Award in 2005. He's co-creator of the Backus-Now form, which is used to represent sort of programming language syntax. The highlighted quotes here, I'm going to read them out to you because I just think it's wonderful, this explanation of programming as theory building. And he says, a main claim of the theory building view of programming is that an essential part of any program, the theory of it, is something that could not conceivably be expressed but is inextricably bound to human beings. So I go on to the last bit. The death of the program happens when the programmer team possessing its theory is dissolved. A dead program may continue to be used for execution in a computer and to produce useful results. The actual state of death becomes visible when demands for modifications of the program cannot be intelligently answered. Revival of a program is the rebuilding of its theory by a new programmer team. This is like pretty profound stuff, right? And I think when I read it and everyone I've showed it to has sort of gone, yeah, this makes a lot of sense. Like this resonates with my experience of working in a team. And we see it, you know, like if we are working in an environment where we don't let teams have ownership of the code and we're just rotating project members through the code, there's no coherent theory of the program and people are spending a lot of time trying to rebuild that theory in order to help them make the changes. Whereas when you see teams that have ownership and a long relationship with the code, they can respond to change requests very rapidly. They know exactly where to make the change because they know it. They have a theory of the program in their heads. So when we think about the outcomes that we're trying to achieve with commercial software building, that knowledge in your heads is a key component of the overall socio-technical system. We can't just look at a piece of code and tell us if it's a good piece of code. If it's something that's going to respond well in an environment that mandates continuous change without understanding the team that is working on that code and the time and space that they have to build and maintain that theory in their heads over time. So I think in the language that I've been using today, we can think about confusion as being an absence of a theory of the system. Building a theory of the system is about reducing our confusion around what we're trying to do and how to engage with the system that we're responsible for. So at the heart of my argument is that a defense of technical excellence is that any practice that helps the team reduce confusion and to maintain and build that theory of the program is a practice of technical excellence. This is at the heart of the whole thing that we have to be doing here. So let's look at some of these practices, my favorite ones. There's many more, but these are the ones that I use regularly and I strongly encourage teams to take a look at them. The first one is event storming. I mentioned this earlier. Event storming is a practice where you get a whole bunch of different people, so domain experts, stakeholders and engineers, you get them all in the same room, maybe just for a day, maybe for half a day, and you get everyone to put sticky notes up on the wall to try and explain and describe the business process that the system is trying to fulfill. The reason it's done in this way, just with orange sticky notes, and there's no like strict formal notation, is that other practices like BPMN and other sort of business process modeling have such strict notation, and UML is the same, that you can't have domain experts engage with and understand and explain to you what's going on. And so in the programming as theory building language, I think about this kind of activity as something that helps the team build a theory about the business domain. Not so much about the code, but about the business and the domain that they're trying to engage with. And what I love about it is that it brings these feedback loops right into the fore, because by working closely with your stakeholders and the people that understand the domain, you get these conversations like, is this what you meant? No, not quite. We meant something like that. And you visualize it very rapidly. You drive consensus. You drive a coherent and shared mental model and understanding of how the business is supposed to operate. So if this sounds interesting to you, I strongly recommend looking up event storming and looking at how these practices work and how you can start to help your team work together with people outside the dev team to build a more shared view of what the thing's trying to do, which in the sort of framework that we're exploring today is, I think, about building those theories about the domain. The next thing I'm going to talk about is a pretty new one. It's called residuality theory. Anyone come across this one yet? A couple of hands going up. Barry O'Reilly has spoken about it at NDC before. He's constructed this idea called residuality, which is kind of like, I mean, it's a bit more than this, but it's kind of like building theories about the business context and about how the architecture might change over time. This was really confronting to me when I first came across it. A random simulation of stress is a better way of generating a software architecture than prediction, requirements analysis, reuse of patterns, or reactive change management by coding. So what he means by reactive change management by coding is like the classic Agile approach where we say, oh, we had an unexpected change, we're going to like code and refactor and evolve the system. So this was confronting to me as someone who's built a consulting practice about helping people do requirements analysis, predict what's going to happen in their businesses, and engage in reactive change management by coding. But you know, once I got into it, I realized that there's really something in here, and I do recommend that you know, you check it out. I'm going to spend a little bit more time explaining this one because it's such a new idea. The idea is that we might have our software architecture, maybe a couple of microservices, and then just dependencies between them. And then what happens in the world is a stressor. A stressor is any kind of thing that causes a problem in the architecture. It might be a requirements change, it might be an availability issue, like a data center down. It's anything that can happen at any time that basically says, oh, this architecture is not going to cope. It's not going to be easy to change. It's not going to stay online. There's a problem. So over time, we have to change our architecture to be more resilient to that stressor, right? And so what Barry says is this change is a critical thing. He calls it a residue. It's what's left over after we've experienced the stressor. And what we often find teams doing is that they wait until the stressors happen and then react. And then they have to have major architectural changes, or they have to deal with complex architectures that are not well suited to the new world that we live in now that this stressor has happened. So what Barry says is the best way to deal with this is to actually go and like list all the possible stresses you can think of. We're not trying to predict exactly what's going to happen. We're just trying to list everything. And every stressor, we assess it in the same way. We say these are equally likely, whether it's Godzilla attacking Paris or customers wanting to pay with different payment technology. We don't care. We're saying they're both equally likely. Obviously, we know they're not actually equally likely. But the problem with when we start to assess or to provide some sort of like guess as to the probabilities is that even though in a case like Godzilla attacking, we can probably be pretty confident that's not going to happen, in a lot of other cases, we're going to get it wrong. And it turns out that just by listing all of them, I've only shown 3 here, but really you would usually end up with like a couple of hundred, is that when you start analyzing them, and you think, well, hypothetically, what would I do? If a stressor hit, what kind of system would we need to cope with it? And you go through one by one and you do this, and you end up with 2 different residues. But what ends up happening is that you start to see more stressors that are actually already addressed by residues that you've already come up with. And this is why it actually doesn't matter whether you say Godzilla attacks Paris, because the residue that you come up with that, for that, is going to protect you from a whole bunch of other scenarios. Maybe it's flooding. Maybe it's a fire, maybe it's some other sort of data center issue, and you end up with abstractions that protect you from a whole range of possible futures. So once you've realized that these are a couple of key residues that are going to give us a broad range of protection, you merge them together into your new residual architecture, and what you can do is you can go and assess all of the stresses that you hadn't yet looked at against your new architecture, and it turns out that pretty much every time anyone's done this, it turns out the new architecture is more resilient to a broader range of possibilities. This is a very different approach to thinking about software design and architecture. There's a lot more to it. I wish I had more time to dig into it, but I wanted to sort of give you this teaser to sort of tempt you into going and reading more about this afterwards, because I think it's such a fascinating idea, and I think that teams that start looking at this are going to find some benefits from it. Another practice of technical excellence that I'm really passionate about is lightweight documentation. I'm not a big fan of like heavyweight documents that are out of date before you've even finished writing them, but I'm a fan of documents that are easy to maintain. And part of that is about making them living documents that are very close to where the team is working. So maybe everyone heard of Simon Brown's C4 model. using Structurizer. It's about documenting your architecture in code. There's another great tool that's out there at the moment. David Boyne has done some NDC talks about event catalog. It helps you visualize event-driven systems, the flow of messages through your system, and it's all driven by like markdown files in your repository. If you want to go even like really basic architecture decision records, just keeping markdown files in your repos that kind of keep track of what are the key decisions that we've made over time, what were the drivers of those decisions, what options did we consider, what constraints were affecting us at the time, what kind of decision outcomes did we make, and what are the consequences of that we foresee. This is a fantastic way of helping teams rebuild their theories over time, because if you do have rotation of team members and the theory gets lost, this kind of documentation is incredibly helpful. And the last one I'm going to mention is actually my passion project. This is a tool I'm building. It's called Contextive. It's about documenting your domain language. So we all work in environments where we have terminology that only makes sense in that business environment. And often developers come in and they think they know what the words mean, but they mean something very special in this context. And so Contextive lets you document that in YAML files in your repository, and it's a set of IDE extensions and browser extensions that give you sort of hover support to understand what these words mean in a given context. And again, it's sort of designed to be lightweight, easy to maintain, and to be embedded into the places that you're working so that you're sort of given the support that you need at the time that you're doing the work. And all of these practices are about rebuilding those theories about the design. Another practice of technical excellence that I'm a huge fan of is bite-sized architecture. It's about knowledge sharing and collaboration. If you are taking on responsibility for a system and maybe you only understand part of it, this is a practice where you can get together. Typically, you only spend about sort of 45 to 90 minutes. For about 5 to 10 minutes, everybody goes and draws their understanding of the architecture, and then you come back together and you try and merge all of your understandings. And the thing that's so great about this, compared to like traditional approaches where you just send the architect off to go and document it, is that when the architect documents it, you only get one person's perspective. And that's always missing things. The developers working on the code often understand the architecture better than an architect, especially if they're not like an active coding architect. And developers working on the code only really understand the parts of the code that they've had to engage with. So getting everyone together, sharing their diagrams and their perspectives and their levels of understanding helps the whole team build a more coherent and cohesive view and vision of the system. So again, it's one of these things that's all about helping the team build that model, that theory of the program and the system in their heads. Test-driven development is another one that I'm a big fan of. To me, this is about building theories about the code, getting right down into it. There's a lot of misconceptions about test-driven development. Sometimes people think it means that you have to write all the tests first. That's definitely not the intention. You write one little test, you make it pass with a little piece of implementation, and then you immediately do some refactoring. So this is great because it lets you clean up the cruft as you go. And it's also great because by writing the test first, you're forcing yourself to build a theory about how the program is actually going to work. And because the tests are now there for other developers to come along and read, it helps them build their theories about the program more easily as well. So another excellent practice. Finally, observability. Anyone using OpenTelemetry in their environments? This is about building theories about the runtime. It's about helping the team make sense of and understand what's actually going on in production. What kind of messages are flowing through your system, what kind of API requests are you getting, where is the system spending its time? So all these practices you can see, like these are the things people know about that you're supposed to be doing. You should be doing domain-driven design with event storming. You should be doing residuality now, I think. You should be sharing like lightweight documentation. You should be doing test-driven development and paying attention to quality. We all know we should be doing these things. We're very rarely given the time to. But what I'm trying to make the case in this talk is that these things have value, and that value is the knowledge in your heads that they formulate, that they help you build. And that is what breaks that sort of vicious loop, feedback loop. So let's look at what happens if we put all this together. We say, let's take that diagram, that sort of mega diagram that I built before. I'm not going to be able to visualize all of these practices. It gets a bit unwieldy in a diagram, but we can illustrate what happens if we start to incorporate them. And when we do this, we're actually going back to Donnella Meadows, who wrote that first Thinking in Systems primer book, because she references this concept called leverage points. Leverage points are parts of a system where you can intervene and get some leverage over the outcome that you're trying to achieve. So you don't have to read the whole thing here. Just a couple of sort of caveats that she says, and I'm going to show you a list of possible leverage points, because she presented these 12 leverage points, but she said, and this is what the reason I want to draw attention to this is a lot of people take these 12 as like, you know, carved into stone tablets, and this is the only thing. But she was very clear, complex systems are complex. It's dangerous to generalize about them. This list is a work in progress. It's not a recipe. it's an invitation to think more broadly about systems change. Now, notwithstanding that, and looking at these 12 that she listed here, all the way from like just trying to change fixed numbers and constants right down to like transcending paradigms and just completely changing the way you think about the world. There's one in the middle, which I think is actually something that a lot of us have potentially the ability to influence. It's a leverage point we might be able to engage with. And it's these balancing feedback loops that we've been talking about. She specifically says that the strength of the feedbacks relative to the impacts they're trying to correct is the key to sort of applying that leverage to drive the system change that you're trying to achieve. So let's look at what happens. Let's introduce, we're going to interact with a leverage point by introducing a balancing feedback loop in the form of a couple of those practices before, specifically test-driven development and collaborative design through, say, event storming by domain-driven design. So it's going to take a little while for everything to filter through. What we see here is we don't have zero confusion. Like, no one's claiming we're going to have zero confusion. But just like that very first sort of balancing loop that I showed you, we have a more sustainable outcome here. We do get periods of time where we have more or less crafts. We have periods of time where we have more or less bugs. But over time, it balances out. We're spending time on test-driven development. We're spending time on collaborative design. We're spending time on adding new value. And that their value is actually getting delivered in a way that is sustainable, not consistently static, but it's going to be there. We're not going to see it drive down to zero and get locked there. We're actually going to be able to achieve outcomes over time. And I think this is at the heart of this whole talk is this idea. And hopefully these sorts of tools will help you visualize and explain to people in your organization why it's important to pay attention to these things. Now, before we sort of wrap up, I wanted to just be really clear also about these causal loop diagrams. What are they not? So I've said they're really great. They're fun to play around with. You draw these diagrams, you see the arrows floating around. It's lovely. But we've got to be clear what they're not. They're not reality. They're not an accurate simulation. They're not objective fact. Like I said before, as I introduced them, they're intuition pumps. You know, we put it another way. All models are wrong. Some are useful. The map is not the terrain. The model is not the thing modeled. These systems, they're not reality, but they can help you work through and make sense of, just as I built them up step by step, looking at them and saying, does this match my intuition? Does this explain what I'm seeing in my day-to-day? And gradually, until you sort of build up a system that looks like, actually, this does look like what I experience, and this is now a tool I can use to explain to others the way I see the world. We also have to address the AI elephant in the room, right? Because everything I've talked about has been about humans writing software, and about 70% of the talks in this conference are about how humans aren't going to be writing software anymore. So how relevant am I? Am I just a dinosaur? I think the key is in that programming as theory building concept, because when we use large language models to write code, where is the theory of the program held? LLMs cannot hold a theory of the program. Every time you prompt an LLM, the whole history of your conversation and all the context that you've provided gets passed in, evaluated mathematically against the model weights, and something else comes out, which might be code changes, might be a response. But there's no theory held in the LLM, and there's no theory held in the context that you're providing. There's just words that have statistical probabilities of being expressed, and there's matches done against the likelihood of those like phrases and words and tokens being found in the model weight, and it's remarkable and impressive what it can do just with that. But there's no theory of the program. The team, the human beings working with it, are the only ones that can hold the theory of the program. And we're seeing this play out in the evidence. There's limited evidence out there so far, but it's slowly filtering through. Dora released a paper last year, The State of AI-Assisted Software Development, and their summary in this was that AI's primary role in software development is that of an amplifier. It magnifies the strengths of high-performing organizations and the dysfunctions of struggling ones. So one way of thinking about this is that there's a baseline 0 point, which many teams are below. And if you're at 5, AI is going to maybe kick you up to 15. And if you're at -5, it's going to kick you down to -15. And I think the only reason this makes sense to me is because of programming as theory building. If you're already building software in a modular way, those modules are smaller. You can provide less context to the LLM to engage with changing that model, and those changes are not going to flow through and screw with the rest of your system. If you're already in practice of doing changes in a small way with tests and quality around it and releasing continuously to production and closing those feedback loops, then you're going to be able to catch the problems introduced by LLMs quickly so that the good stuff can flow through and the bad stuff gets caught. So when they say high-performing teams, they mean teams that are already doing all the stuff I just said. They're the ones that are going to get the benefit from engaging with LLMs. And if those teams are not doing that and they're stuck in those reinforcing feedback loops, all the LLMs are going to do is they're going to be like a rocket fuel on that negative reinforcing feedback loop and drive you further down into decay. And this is what the evidence has shown. And there was another research from META, the Model Evaluation and Threat Research. So they measured the impact of AI in early 2025 on open source developer productivity. Anyone see this paper? It's a fascinating result. When developers are using AI tools, they take 19% longer to complete issues. The gap between perception and reality is striking. They expected it to speed them up by 24%. Even after it took them longer, they still self-reported that it had sped them up by 20%. We are not good judges of our own experiences. When it was objectively measured, the outcomes were not great. When you put that together with the DORA report, I think this actually says that everything I've shared with you today is even more important than it ever has been. If you're getting these expectations to engage with LLMs and you're not engaging in practice of technical excellence, you are going to find, as Dora found, that it becomes an amplifier of your dysfunction rather than rocket fuel on the outcomes. This is all well and good. We've got some data, we've got some statistics, we've got some numbers. I'm sure that these are going to keep changing and the models keep evolving and the products keep improving. So tell us what you really think, Chris. Well, my friends, we do not have the minutes, hours, or days for me to rant at you about my frustrations with the way large language models are being commercialized and sold right now. And I'm very precise with my language there, the way they're being commercialized. I have no problem with the technology. The technology is fascinating. I love it. I have a big problem with the way they're being built and sold. I have ethical issues with it. I have massive risk concerns that are not being addressed. So I spoke about this last year in a talk called AI is a hype-fueled dumpster fire that will burn down the planet and get you thrown in jail. I know the title's a little subtle. So to be clear, this is my attempt to assess ethics and risk. It's not about can I write good code with it? It's about should I engage with it? Does it align with my moral values to engage with a product that is consuming energy at an ever-increasing rate in an era of climate crisis, that only exists because of wholesale massive data theft from the most vulnerable in our society that can't protect themselves, that has exploited data workers in the global south to kind of protect the global north from like harmful outputs of AIs. It doesn't align with my ethics. And so I'm actually quite proud to say I'm an LLM vegan. I don't engage with LLMs at all. But I'm very fascinated by them and I am following closely the research and all the reports, and I have to help teams engage with this stuff because it's not going away and people are also not recognizing it. But anyway, if any of what I just said resonates with you, check out this talk, you might enjoy it. Or maybe you really love AI, but you really enjoy the violent sensation of someone disagreeing with you, then you might check this one out too. But let's get back to the thing. Let's go back to our team who finally has been able to explain the sort of cause and effect relationships in these feedback loops and has been given permission to engage in some of these practices, to do some design work, to write some documentation, to do TDD and actually get some quality control into their processes. So we have our team, we get our stakeholder, a new requirement gets thrown in the backlog. The team starts work, they get started. Quality control comes along and finds a bug. And you know what? We just fix it. We just fix it straight away. We go to production and the bug is not there and that feedback loop doesn't get kicked off. Feels nice, right? Maybe they come along with a new feature, goes into the backlog. Team comes along, starts coding. They get given the chance to do some domain analysis. They get access to stakeholders and domain experts to sit in a room for a couple of days, putting sticky notes on a wall and building a mental model, building a theory of the domain and getting started on it. And it goes to production and there's no stinky pile of garbage in the corner. Feels good. So what are the key takeaways here? Takeaway 1, the iron triangle does not work for software. If you want to use it, apply it to external quality only and preserve internal quality at all costs, because internal quality has a direct cause and effect relationship with confusion. And technical excellence is any practice that protects the theory of the program held by the team, that reduces that confusion quantity, which is that key node in the reinforcing feedback loop that screws everything up. And finally, causal loop diagrams, they're fun to play around with, a helpful storytelling device. Use them to pump your intuition, explore your environment, shape a narrative, make the case for what you believe is the right thing to do. Do not mistake their visualizations for objective facts. They're not simulations. It's about exploring collaboratively with people to build consensus and a shared understanding of what's going on. This QR code will take you to my website. There you can see all the slides there and a whole bunch of links to books and papers, references that I've referred to through this talk. I'll leave it there for a second while QR codes get scanned. And if you ever want to chat about this stuff, I'm very happy to connect. Just go to my website, go down the bottom, links to LinkedIn and Blue Sky and all the usuals. And please reach out for a chat. I love to talk about all this stuff. And the final thing I'm going to say in relation to that, just inviting people to connect with me, and this is a little bit of a detour, but I have been for a little while offering like I don't want to call it a service, it's not really a service, but I'm one of those people who believes that I've been very fortunate to have an immense amount of privilege in engaging with the world, and I see that very starkly in our technology sector because there are many people who are discriminated against systemically for a whole bunch of reasons. And so a little while ago, I decided that I'm going to go on like a journey of trying to be a better ally to these people. And if you're someone who also would like to be a better ally to people who are affected by systemic discrimination, please reach out. It's like a peer support kind of conversation. I don't claim to be an expert in it. I'm working it out myself, how to do better. But if anyone wants to talk about how you can do better, supporting people in your organisation and just being a better ally and partner to people who are affected, please reach out. I'd love to talk about that topic too. So that's it from me. Thank you so much. Enjoy the rest of the conference and yeah, have a lovely day. Thanks for coming.